Hi, hello pre-calculus and welcome to chapter 3. And we're going to be working on exponential, logistic, and logarithmic graphs. So let's go ahead and get going. So what we're going to do, this is a little bit of review. We're going to look at some exponential graphs. First. This first introduced to you way back in advanced algebra. And what I can tell you is that what you would have learned back then is that in an exponential function, you would have had like something f of x equals a times b to the x power. Okay. This a value, the a value is the y-intercept. That'll tell you where it crosses the y-axis. Okay? The b value is either a growth or a decay factor. And what you may remember is that if that b value is greater than 1, okay, it is growth. And if that b value is between 0 and 1, it is decay. Okay, so that's some basic advanced algebra material you would have had in the past. Okay. We'll just also say that b can't be 1 because if it's 1, you won't have growth or decay at all. It'll just be a line. So just a good little practice on these graphs. Recognizing them, we want to be able to recognize if they're exponential or not. Okay, so first of all, this a certainly is. That's in the form, we got f of x equals, it'd be like 1 times 3 to the x. This one is not because the x is not in the exponent. This one right here, again, we can kind of just parse it out a little bit. This is h of x equals, I got negative 2.1, that's the a value, and then times 1.5 to the x. That certainly is. It'd actually be a growth model. All right. This one right here, now there's a little trick here. In this one, there's a negative x up there. You got to remember what negative exponents do. So if you remember what a negative exponent does, if I had something like x to the negative 1, that's the same as 1 over x. They just flip. Okay? So really this one here is like k of x equals 7 times, and then I'd flip that number to be 1/2, and then it'd be to the x power. So this is actually a decay model, even though it may trick you and looks like that b value is above 1. Well, it's really got to that negative exponent. It's like 2 to the negative 1 in there raised to the x. Oops. And this next one, again, would be, again, let me circle that there because that's exponential. This one here, too, is also exponential. Simply j of x equals 5 times 6 to the x power, so it does fit that form. All right. So we kind of keep going here. We're going to identify these as growth or decay. Again, looking at that b value, that's bigger than 1. This is growth, and there's no negative in that exponent of x. This one here, again, that's between 0 and 1, so this would be decay. So again, always looking at that number right here, that b value. So here it looks like that b value looks like it'd be growth, but remember here we got that negative exponent, which would actually flip that. So this would be like 1/2 to the x. So this is actually decay. Same thing here with this one. This would be y equals 3, and we'd flip that fraction because of the negative exponent, and this would be growth. All right, so get a little practice here down these bottom ones. Identifying first if it's growth or decay, and then identify the growth factor. So this one, probably easier to do this one down here, the second one. That number is bigger than 1. There's no negative in that exponent, so this is certainly growth. and its growth factor would be 1.353. This one here, its actual growth factor would be 1 over 1.353. And if you just divide that in the calculator, it's approximately 0.739. So that's a decay, because that's between 0 and 1. Same thing down here. This one doesn't have a negative exponent. We're looking right there. That's between 0 and 1, so that is a decay. And its decay factor is 0.48. This one, again, now look at that negative exponent, so it's really like 1 over 0.48, which is approximately, if you use your calculator, 2.083. And so that'd be actually a bigger number, bigger than 1, so this would be growth. All right, let's move on. As we look at the next part, we're going to look at those graphs of exponentials. All right? And we know again, as if this a value is the y-intercept, this would intercept at some a value on the whatever that is on the y-axis. So if these are growth models, they will do this. They generally look like this with an asymptote here at y equals 0. So I can put that down here. Got a horizontal asymptote at y equals 0. Let's go back and look at this domain and range stuff. Domain, this does go infinitely to the left and to the right. The range, the lowest it goes is 0, but the highest it goes is infinity. This is continuous. In other words, I can keep my pencil and never have to pick it up. Symmetry, it has none. Its intercepts, it does have a y-intercept, does not have an x-intercept, and it'd be at the coordinate 0, and then whatever that a value is. Here it depends on what, again, that a value is. Here the limit, let's just put this near as x goes to negative infinity. So as I go to negative infinity, as this graph goes this way, as x's go this way, the graph goes, it approaches 0. As the limit of x goes to infinity, so in other words, as I go this way, the graph continues to go up to infinity. Go back up here, bounded above or below. It does have an absolute bottom to this, so this is bounded below. And then the extrema, well, there are no local extrema here, no local minimum or no local max to this problem. This exponential decay, again, it would still cross at this a value, whatever that happens to be, but now decay comes in and levels off like this. So our domain is still the same. It's from negative infinity to infinity. The range, still the lowest it goes is 0, and the highest it goes is infinity. It is continuous, so I don't have to pick up my pencil. There is no symmetry. The intercepts, it still has a y-intercept at wherever that a value happens to be. This is still bounded below, because it does have a bound on the bottom. It doesn't go any lower than that. Which means, yes, there's an asymptote there, a horizontal asymptote at y equals 0. There are no local extrema. There is no local minimum or local maximum in this graph. The limit here as x approaches negative infinity. So again, as I go this way in the x direction, the graph goes up to infinity. And as I go this way, x goes to a positive infinity, the graph levels off at 0. All right, so kind of a quick review of that back from advanced algebra. Let's go back and see if we can look at some of these transformations as well then, and kind of remember what they do. So if we look at this one, now this little movement up here is up there with the x value. So you can kind of think about putting that in parentheses. Remember, we think about when things are in parentheses like this, we think opposite. And this is minus 2, I think. So I think about moving it plus 2 or to the right 2 for that graph. Okay, so I'm going to go This one would be to the right 2. Again, I started with 2 to the x, so I still have the 2 to the x, so I'm not doing any other changing to that. Here, I've just got that negative inside there by the x. So remember, when it's inside with the x, it reflects over the y-axis. If it was out front, and if I had something like h of x equals negative 2 to the x, that was the negative was out front like that, that would reflect over the x-axis. But for this one here, we reflect over the y-axis. This last one here, we've got a number out front. So that talks about how we're going to stretch things vertically. So this is a vertical stretch of 3 times. So if I'm going to practice just doing some sketching here, I look at this first one, that 5 tells me that's been vertically stretched 5 times. Or, I'm sorry, no. Sorry, that's where the y-intercept is. So let's just go 5, 10, 15. And it's been vertically stretched 3 times. Okay. Sorry, it's got a growth factor. So that's a growth factor of 3. And that's our y-intercept. So sorry there. So this graph is going to be, since it's growth, it goes through that y-intercept at 5. Okay. This one right here, this is going to go 5, 10, 15. This is decay. So this is a decay of 1/4. And again, that's our y-intercept right there. So this is going to come through at 15 and then level off. All right. Well, let's look at a very specific example of exponential growth. And look at the function y equals a times e to the x. So some of you might remember this e value. It's called Euler's number. All right. And we do have an approximation of 2.71826. So this is actually the formula on how E is actually calculated. So I remember a long time ago in advanced algebra doing a problem like this to illustrate this in terms of investing of $1 and different interest rates. But what we just need to know is simply that this E value here is 2.71826. Goes on forever. It's like a number like pi. But it certainly is a number bigger than 1, so it is simply a growth. So this is growth, exponential growth. So so this limit, if I do this limit, if I keep doing this, it should get closer and closer to that E value. So the limit is approaching 2.71826, which we simply abbreviate as the letter E. Right? This is really a big thing when you get to calculus. So we'll do a little bit with that as well here in pre-calc. So if I look at this graph, again, this would be the y-intercept. So it'll go through at some a value. And again, this E, because it's bigger than 1, is just simply a growth. So it's going to come through and it's going to grow. So it's just a very specific type of exponential growth using E as the growth factor. So, our domain is still negative infinity to infinity, and the range is still 0 to infinity. Yes, this is continuous because I never have to pick up my pencil. No, there is no symmetry. The intercepts, there is a y-intercept at 0 and whatever that a value happens to be. This is, again, still bounded below, because, again, it doesn't go any lower than that. Which means there is an asymptote there, a horizontal asymptote at y equals 0, and there are no local extrema. And again, the limit as x approaches negative infinity. So as I go this way, the graph's going to level off at 0. And as x approaches positive infinity, as I go this way, this graph goes up forever to infinity. Okay, so we're going to look at some of the transformations on this specific graph of the graph f of x equals e to the x. So again, notice here my a value would actually be 1 out front. So what we're going to do is we're going to describe this graph, see what happens, and kind of give a quick little sketch of this. So again, because you see this up here, that's in the exponent with the x, we think opposite. So this would actually be going to the left 2. So I'm going to take that original exponential growth, which we crossed here at our y-intercept of 1, and just got to move it to the left 2. So 1, 2, so it should cross right there. And it'll kind of go up like that. Okay. This one right here, that negative is out front. That negative is out front. It's not up there with the x. So this flips over the x-axis. So I'm going to take that original graph that went here through at 1. It was a exponential growth, and it's going to flip over this x-axis. So now it's going to come through here at negative 1 and do that. This graph right here, now this is not with that x. Okay, so it's outside of that. So that's telling us how it's moving up or down. And again, because it's not grouped with that the y value over here, we can do as is. So this just moves it down 1. So again, normally it's here coming through an exponential growth coming through at 1. It's now going to come through at 0. And again, it had its horizontal asymptote there at y equals 0. Now that horizontal asymptote is right here at y equals negative 1, because that moved down too. So this graph just kind of comes through like this. All right, let's move on to logarithmic functions. Logarithmic functions. So we start looking at our log functions. Log functions are simply just inverses of exponentials. So here we have our exponential growth model. And if we just flip it over the line y equals x, we have our log model. All right. So we can look at that as a table as well too. So if I had my exponential growth model and created a table of values for this, really what happens is the x becomes the y and the y becomes the x, and we've got a new table here for our log. So when I look at this, I've got y equals 2 to the x. The inverse of this would be a logarithmic function, as y equals log base 2 of x. You notice those two numbers are the same. Okay, so we're going to kind of look at the graph of this. And a logarithmic graph will cross here at 1, come up, and it'll go like this. All right. So generally, if I look at the domain of this, the domain is really just what the range was of an exponential. So the domain here is from 0 to infinity. The range is the same as what the domain was for an exponential, so it's negative infinity to infinity. Yes, this is continuous because I never have to pick up my pencil to draw this. Symmetry, there is none. Okay. The intercepts now, instead of having a y-intercept, it does have an x-intercept, and that would be right here at the coordinate 1, 0. Bounded above or below, this is not bounded. It's going forever down and forever up. Asymptotes, well, there is one right here, and that's a vertical asymptote at x equals 0. And in regards to the extrema, again, there's no local extrema. There's no local minimum or there's no local maximum. Now here, the limit, here as I go, as the limit goes, as x goes out to positive infinity, this graph's going to continue to go up to positive infinity. But here, we can't go to negative infinity here. So if I look at the limit of f of x as x goes to negative infinity, I can't get there. I can't do it. There's a wall right here. There's a vertical asymptote in the way. So this doesn't have a limit as x approaches negative infinity. It does have a limit as x approaches 0, and that'd be negative infinity. But when we're looking at end behavior, we're always looking at it as it approaches infinity or negative infinity. So let's take a look at some of the transformations then, and being able to describe these as well, and then give a quick little graph. Now, with this one, what I would do is I would factor a little negative out there. So this is natural log, and I'd take a negative out. So this would actually be then positive x, because that'd be, you take the negative out of negative, so positive, so take a negative out of positive 2 would be minus 2. Because this way I can kind of see this piece. I can see this piece right here, which tells me, because it's inside there, that this is a flip over the y-axis. And this piece right here would tell me that it's moving to the right 2. So what I got to do is I got to take that original logarithm graph, flip it over the x-axis. So if I start here and I flip it over let's flip it over the y-axis. It's like that now. And then I got to move it to the left too. What that graph would look like then. So again, have this graph, flip it over, move it to the right 2. So if I had it here, it's crossing at 1. If I flipped it over, it's crossing at negative 1. Move it to the right 2. So this graph is going to look something like that. This graph right here, or this equation here, maybe what I do is just kind of rearrange this. Put that negative 3 ln of x, and then put that plus 2 over here, because then this tells me this goes up 2, and this negative 3 over here, the negative is up front, so this flips over the x-axis, but it also has a vertical stretch of 3 times. Okay, so I'm going to take the original logarithm graph, which was like this, and then I'm going to flip it across the x-axis. Okay, so now it's going to be something like this. Okay. And then I'm going to stretch it 3 times, so now it's going to probably be more like that. And then I'm going to move it up 2. So this point right here at 1, 0 is going to move up 2, so now it's at 1, 2. So I'm going to erase that and redraw everything. Again, going back here, this is at 1, 2. Yeah, let's remember it was going like this. I flipped it over the x-axis and then stretched it 3 times. So this graph is going to go through that point right there and then kind of curve out like that. All right. I'm sorry for the small printing on these ones here, but I'll rewrite those. And so A is g of x equals ln of x plus 2. What we're supposed to do here is just describe the transformation. This one's inside the x, so think opposite. So this one is just going to the left 2. Letter B was h of x equals ln. Now again, I'd probably factor that negative. So do a negative and then x minus 3. Because then I can say that this is, again, inside by the x, so it flips over the y-axis and then moves to the right 3. So you can see this graph translation theorem we learned a long time ago is really coming in handy. Letter C is just g of x equals 3 times log of x. You know, that one here is just a vertical stretch. So 3 times. And then letter D, if I look at maybe rearranging that one too, this is an h of x equals log of x plus 1. So this one will just go with 1. Some more practice over here. So if I look at this, again, that's inside by the x, so that's going to go right 1. This one here is outside of the x, so it's associated with the y, and it does as is. So this will go down 3. This one here, again, now always remember too, our order, we always think about, I always think about when we get up in the morning, our alarm goes off, we flip over to turn it off, we stretch, and then we walk out of bed, so which we translate. Okay. So that's, I'm going to address that negative part first. So that negative part's out front, it's not within the x, so that flips over the x-axis. And anything else is that adjustment inside here by the x, so think opposite. So this would go to the left 5. All right, so a good review there of logarithms. Okay. So we got one more page to do here. And we're going to look at logistic functions. This one is brand spanking new. This is one you have not seen before. So what I want to emphasize here is the general form of a logistic. Okay? I'm going to write that just maybe just a little bit differently as we kind of go through here. But generally, this logistic is f of x equals c. Oops, maybe I should draw that a little better. It looks kind of funky little letter. It is c over 1 plus it'd be a times b to the x. Right? That's probably the more common form here. I'm sorry, it should have been this one right here. So we won't use that one. We'll use the f of x equals c over 1 plus a times b to the x, because this little piece looks like our exponential model. Okay, but now remember, this is on the bottom, and so this is going to be, you have to think a little bit of the opposite, because if it's on the bottom, we'll talk about that in a few minutes. This c value here, this c value is called our limit to growth. Okay, so that kind of talks about how big it's allowed to grow to. That's how the biggest it can get to. Okay, so now again, this piece right here, normally we think that b value, when it is greater than 1, it was growth, but now it's on the bottom, so it's in the opposite spot. So this is actually, when the b value down here is bigger than 1, this is actually decay. And when that b value is less than 1, it is actually growth. Okay? So let's look at this example right here. Y equals 1 plus e to the negative x. Wow, so that one's kind of interesting, because when I look at the e value, remember that e value is approximately 2 point, so that's a little clearer there for you. Number e, oops, is approximately at 2.718. So the e value is bigger than 1, but now we have that negative in there too, so that e to the negative x is really like 1 over 2.718 to the x power. So this is actually, when I look at that, here's this number. This is less than 1. Okay, so that would be a growth model. So this is going to grow. It's going to get bigger as we move from left to right. So just to kind of give you the general gist of this, of what a logistic equation looks like. Okay. in this case right here, this is the 1 value. That's that limit to growth. That's the highest it will go. So let's just kind of label that 1. And the halfway between this, this value of 0 and 1 is 1/2. All right, that's going to be the y-intercept, and we'll talk about that down here in a second. But I just want to kind of give you the general gist of what this graph does first. It's going to kind of come in like this, and kind of lane change this way sideways. And that's what a logistic graph does. It's really, going back, it's kind of like what I call realistic growth, because if you look like a plant growth, like a tree, it's going to be real small at first, grow real quickly, and then kind of level off. Trees don't grow infinitely, or for that matter, even our own growth. We start off as a single cell organism and start growing, and then we eventually level off as well too. So let's just kind of give some general ideas about these logistic graphs. Okay, logistic graphs. Again, that's going to level off right here at this, and it also has this asymptote there too. So when I look at the domain of this, it does go left and right infinitely. The range in this case here is from 0 to 1, and it doesn't touch those. Continuous, yes, this is continuous because I don't have to pick up my pencil. And here's kind of a little tricky piece with the symmetry. It does have rotational symmetry here. If I do rotate this 180 degrees, I would land on it. So this does have rotational, actually you should say 180 degree rotational symmetry about the point, that coordinate there of 0, 1/2, which happens to be the y-intercept there as well, which is 0, 1/2. And there are no x-intercepts because of that asymptote there. This is bounded both above and below. It's got here and here. The asymptotes, so yeah, if it's bounded above and below, there's 2 horizontal asymptotes at y = 1 and y = 0. There's no local extrema. There's no local maximum or local minimum, only the absolutes. And here now the limit as x goes to negative infinity, as I go this way, this graph's going to level off at 0. As the limit as x goes to positive infinity, as I go this way, the graph's going to level off there at 1. All right, so I want to talk a little bit about growth models and decay models. So again, I want to emphasize to you that in the setup that f of x equals c over 1 plus a times b to the x, and if that b value is less than 1, it is growth. So I can see that here, that b value is less than 1. The x doesn't have a negative in it, so that certainly has a b value between or less than 1. Here, again, you look at that e to the negative 3 as my b value. So again, that's 2.718 to the negative 3. But again, if we flip that, because it's a negative, it'd be like 1 over 2.718 to the third power down here on the bottom. That's a number between 0 and 1. It's less than 1, so that is growth. Where here, again, you can see that b value is 7. So when I have f of x equals my limit to growth over 1 plus a b to the x, and when that b value is bigger than 1, in this case, because it's down the bottom, this would be decay. So here we see that b value is 7 there, so that's decay. Here, again, you have e, e to the 3x, so e to the third, certainly a number bigger than 1. It's 2.718 to the third, so that's certainly bigger than 1. So that's decay. But lastly, what I'm going to do is just be able to graph these functions, sketch them real quick. And again, realize this is my limit to growth. That's my limit to growth. So that's, in other words, that's the highest I know that it will get. So if I'm going to sketch this graph, I know that the highest will go here is 8. So let's find the other, or the y-intercept for that matter. All right. So to find the y-intercept, that's the first thing we want to do here is find that y-intercept. You're really finding f of when x is 0. So you get 8 over 1 plus 3 times 0.7 to the 0 power. Well, anything to the 0 power is 1. So this would be 8 over 1 plus 3 times 1, which is 3. This is 1 plus 3 is 4. 8 over 4 is 2. So my y-intercept would be, so you say y-int would be at 0, 2. Okay, so that's where the y-intercept is. My lower value, the other horizontal asymptote, that I have here would have to be the other horizontal asymptote would be down here, again, because we're looking at growth at that 0 spot. So our two horizontal asymptotes, okay, why isn't this writing here? Would be at what's going on here? But the horizontal asymptotes here should be at y equals 0 and y equals 8. So I apologize on why that's not writing. I'm not writing right now. So maybe it'll work on this one. So let's go and try to find the y-intercept. And maybe if I just change colors here. Sorry. All right, there we go. Be able to fix this here. So again, our horizontal asymptote is right here and right here. So at y equals 8 and also at y equals 0. So there we go. Let's get a clean start here. So we want to find oops, let's go back to this graph. It'll come through like this, come through the 2, and then level off like that. This one here, let's find the y-intercepts. We're going to put 0 in for x. That's 20 over 1 plus 2 times e to the negative 3 times 0, which is just to the 0. Well, e to the 0 is 1, so 2 times 1 is 2. So this would be 20 over 3 would be my y-intercept. So my y-intercept is at 0 and 20/3. All right. Again, now this is my limit to growth. So that's the highest it's going to go is 20. And because we have that 0, you can't get 0, but that's the smallest, that's the lowest limit. We'll have a graph that looks like this. And this is that's my limit to growth here is at 20. Okay. Here's my x-axis there. My y-intercept is at 0 and 20/3, which is about 6 2/3. So right about here. So that's 20/3. So this graph is going to come in like this, hit that y-intercept, and can then level off up there like that. All right, that's all we got for lesson 3.1. We got several problems we'll be working on for a couple days, and hopefully these notes will be beneficial to you. Thank you for your patience while I was figuring that last little piece out why the technology wasn't working. and we'll see you in class.